The Moon has been our faithful companion for 4.5 billion years, scarred, silent and unchanging. Or so we thought. New research is revealing something surprising. The Moon is getting cratered faster than we ever realized, and the implications reach far beyond the lunar surface. Hey, space family! Welcome back to D3, Discover Deep Dreams, your educational gateway to the cosmos and beyond. I'm your co-captain, and today we're talking about something that is quietly rewriting what we thought we knew about our closest cosmic neighbor. Why is the Moon getting cratered faster? What's causing it? And what does it mean for our plans to return humans to the lunar surface? Let's find out. For decades, scientists believed they had a pretty good handle on the rate at which meteorites and space rocks slam into the Moon. The lunar surface is a geological record going back billions of years. No atmosphere to erode craters, no tectonic activity to erase them. Every impact is preserved, every scar tells a story. By studying Apollo mission samples and analyzing crater counts, scientists built models predicting how often new craters form. The Moon was essentially a slow, steady cosmic punching bag, taking hits at a predictable, manageable rate. That picture has changed dramatically. In recent years, scientists have been able to compare before and after images of the lunar surface taken by NASA's Lunar Reconnaissance orbiter, a spacecraft that has been photographing the Moon in extraordinary detail since 2009. What they found was startling. New craters were forming at a rate significantly higher than the models predicted. Not just slightly higher, dramatically higher. Some studies suggest the current cratering rate is up to 2 times higher than scientists previously estimated for certain size ranges of impacts. But it wasn't just the craters themselves that surprised scientists, it was what was happening around them. Every new impact doesn't just create a crater, it sends material flying across the lunar surface in all directions. These secondary impacts, called ejecta, spread across enormous distances, churning up the top layer of lunar soil called regolith. Scientists discovered that this secondary disturbance is far more widespread and far more significant than previously understood. The Moon's surface is being rearranged, constantly, actively, and faster than we thought. So, why is the cratering rate higher than expected? The answer involves several factors working together. First, our models were simply incomplete. The early estimates were based on limited data. As the Lunar Reconnaissance orbiter accumulated years of comparison images, the true picture became clearer. We weren't seeing a sudden increase in impacts. We were seeing the limitations of our previous models corrected by better data. Second, secondary cratering is more significant than realized. When a large meteorite hits the Moon, it doesn't just create one crater. The ejecta it launches can travel hundreds of miles and create thousands of secondary craters. These secondary impacts were being undercounted in earlier models. Third, there may be variations in the density of meteoroids in different regions of the solar system that our models didn't fully account for. Space isn't uniformly filled with debris. There are streams, clusters, and regions of higher density that the Moon periodically passes through. Here's where this gets critically important for the Artemis program and future lunar habitation. Every crater represents an impact. Every impact on the lunar surface could be an impact on a lunar habitat, a lunar base, or a lunar hotel. Understanding the true cratering rate isn't just an academic exercise. It's essential engineering data for anyone planning to build on or live on the Moon. The revised cratering rates mean that lunar structures need to be designed with higher impact resistance than previously planned. Habitats will need thicker shielding, equipment stored on the surface will need protection, Landing pads and surface infrastructure will need to account for the constant rearrangement of the regolith by new impacts and ejecta. It also means that any equipment left on the lunar surface, including the Apollo landing sites themselves, is being gradually degraded by micrometeorite impacts and ejecta disturbance. The famous boot prints left by Neil Armstrong are slowly being erased, not by wind or water, but by the constant rain of cosmic debris. Here's the profound part of this discovery. The Moon and Earth share the same cosmic neighborhood. The same meteoroids that hit the Moon are hitting Earth too, or would be if Earth didn't have an atmosphere and magnetic field to protect it. By studying the Moon's cratering rate, scientists gain insight into the impact history of Earth itself. Many of the impacts that shaped Earth's geological and biological history, including the one that wiped out the dinosaurs, came from the same population of objects that continue to hit the Moon today. The Moon is Earth's cosmic shield and Earth's cosmic mirror simultaneously. It absorbs impacts that might otherwise reach Earth, and it records the history of those impacts in its ancient, unchanging surface. Understanding the Moon better means understanding Earth better. Understanding the impact environment means understanding the risks and the history of our own planet. Scientists are continuing to refine their models using ongoing data from the Lunar Reconnaissance Orbiter and other lunar missions. As the Artemis program establishes a sustained human presence on the Moon, direct surface monitoring of impact events will become possible for the first time. Seismometers, like the ones placed on the Moon during the Apollo missions, detected lunar impacts directly. Future seismic networks on the lunar surface could provide real-time monitoring of impact events, giving scientists the most accurate picture yet of the true cratering rate. And that data will be invaluable, not just for science, but for the engineers designing the habitats, the roads, and the infrastructure of humanity's first permanent lunar settlement. The Moon has been keeping secrets. For 4.5 billion years, it has absorbed the impacts of the solar system in silence, recording every hit in its ancient surface. Now, for the first time, we have the technology to read that record in real time. What we're finding is that the Moon is more dynamic than we thought, more active, more alive with cosmic energy than its silent face suggests. And as we prepare to send humans back, and this time to stay, understanding that dynamic environment isn't just fascinating science, it's the difference between a habitat that survives and one that doesn't. The Moon is talking, and we are finally learning to listen. If you like space exploration, don't forget to like, subscribe, and ring that notification bell so you never miss a single D3 episode. Keep looking up.